This is lesson number 8 and the Ethernet IP core. This tutorial will be talking about the receiver's address checker. The verilog code can be found here. Project fpga.com/tcp select address checker. Then you'll be able to see the verilog code. I'll be explaining this code in Logisim. This is the circuit for the address check. So what this code is doing is to check the address, the receiver's address, to know if it matches the address of the host. That is to say, whenever a host receives data, it has to check if this data actually belongs to it. So it's going to, at the end, it's going to generate two signals: address mix and RS abort. So this RS abort and address mix shows that this address does not actually belong to the particular host that received the message. So RS abort is a signal saying that this frame reception should be aborted, that this frame is not meant for it. And we know, when in the project introduction we talked about the different addresses, the different receivers addresses. Yes, type of Ethernet addresses: the unicast, the multicast, and the broadcast. So in this tutorial we'll be seeing how these different addresses are being implemented. At this point, the receiver is going to check the received address with his own MAC address. So this is how the host checks for frames, to know this frame I'm receiving, does it belong to me or does it belong to another host. So I will divide this circuit in section. This whole section actually checks for unicast address. It checks is the destination address my MAC address. If it's not the host MAC address, it's going to abort it. This part checks for the multicast. For the multicast address, that is, if it's being sent to more than one host, it's going to check if it's among the hosts that is meant to receive it. And this is just for the broadcast, and this particular place checks for the broadcast. So I will treat them section by section. Let's talk about this unicast address for a start. So one of the things you are going to notice is, when are you going to check for the address? When you are receiving a frame. So this is the frame. You are going to receive the preamble, the SFD, then the destination address. So you have to start checking for this address immediately after the SFD, that is doing the data reception, state data. And you know, during the receiver state machine, we talked about when does this actual frame reception start, when does this Ethernet frame reception start. And we found out that it starts doing the state data, and we know that the state data are 2, 0, and 1. So you are going to check it doing this state data. Whenever you are in this state data, that is when you are going to start checking for the destination address, to know if this frame, the destination, does it belong to me. If it doesn't belong to me, discard it. So you are going to start checking when you are in state data. So here, this is the MAC address. This MAC address is stored in the register. The MAC address of the host is stored in the register. So it's going to compare it against the received data. This is the neighbors you are receiving. This are the neighbors we are receiving, but here is no longer neighbor, is bytes, because when you receive them neighbor by neighbor, the receiver matches them. You receive one neighbor in one state and another neighbor in another state, so it merges the two, and that is how we get this RX data. So this RX data comes from the MRSD, which we treated in our last tutorial. So when you combine two MRSD, one MRSD, the next MRSD, you get one state data, you get one RX data, then another MRSD, the next MRSD, you get another RX data. So that is how we get these bytes. And we remember the byte count that does this. It counts them byte by byte. It no longer counts them neighbor by neighbor. So we are going to see in our next tutorial how we merged two neighbors to get the RX data. And that is why our counter, which we treated, is no longer neighbor count. It's called byte count, because it doesn't count the two states. It counts only one of the states. So that's how we get this neighbor and byte counts. So this is what happens here. This series of AND gates is what does the checking. And for it to check, it first of all make sure that number one, that is in the state, is in either of these states. You see, either of these states, it must be either, it has to be in the state data. Then it checks them doing the byte counting. So it checks when is byte 2, byte 3, byte 4, byte 5, byte 6, byte 7, byte 4. It checks all the bytes. So it compares them one after the other. So whenever it's in byte 2, let's see what happens in byte 2. Whenever it's in byte 2, this AND gate comes on and turns on this multiplexer. So this multiplexer is going to take this value here. So what does this comparator do? It compares the received data at that point with the last, because it comes from the LSB. The received data starts from the LSB, so it checks the last 8 digits, or the last bytes of our MAC address. It compares them, because the RX data has already started sending in our MAC address byte by byte until it completes. The MAC address is 48 bits. We have a 48-bit MAC address. So the RX data is going to check them. It's going to, cause this comparator compares them byte by byte, all of them. But now you see this whenever this byte 2 comes on, this first multiplexer here, when byte 2 comes on, this first multiplexer uses this comparator and compares it with the last 8 bits. That is, the last byte of our MAC address is compared with the first RX data. Then if is okay, if they are equal, it sends a 1 bit here, that is okay. Then on the next clock cycle, that is when we are now counting byte 3, this multiplexer here, this one turns on again and compares comes here and compares the next byte with the next byte from the MAC address with the next received data that is coming in. And if it's okay, it now checks again whether the last one we did, is it okay. That is the essence of this signal that comes back from here and loops back. It makes sure that now this comparator is okay. Then with the last check, the last time we checked, is it okay too? If it's okay, yes, it's okay. It sends a 1 bit signal back into this flip-flop. Then the next cycle again, the flip-flop returns the last value again. That is to say, if any of the checks, if one of the checks fails, let's assume, okay, let's assume that this first check fails. That means every one of them is going to fail. That is, whenever one of the whenever one of the comparison fails, like if the first one fails, that means every one of them is going to fail, because the output of this last check is being fed back again using this AND gate. You see, this signal feeds back the last output from, it uses this D flip-flop here to feed them back and make sure that every single one of them is correct. That is how it checks the received data to make sure that it matches with our MAC address. That is what this place does. It compares the RS data with the MAC address for every byte count. Each of the byte count, by one is byte 2, it checks byte 3, byte 4, byte 6. It compares them byte by byte until the 48 bits of the MAC address have been compared byte by byte with the RS data. So therefore, we can call this signal here, unicast OK. That is a unicast address because the destination address is our MAC address, so it's a unicast message. This signal here means unicast is OK. That is a unicast address since the destination address is our MAC address. Then we also have the broadcast. That is when the sending host sends data to every other host on the network. It is not sending it to a particular network, it sends it to every other host. At this point, it's not going to have our MAC address, it's going to have the broadcast address. That is at this point. So I'm going to show you how this broadcast bit is being generated in another tutorial. This, whenever is a broadcast, this signal here comes on, this broadcast signal comes on, and for us to receive this broadcast signal, there is this ALBO. This ALBO signal comes from our register. We have to set this ALBO R_BO broadcast to 0. If we set it to 1, it means reject all broadcast frames. That is, if you receive a broadcast frame and in the register you set your ALBO to 1, it's going to reject it. It rejects broadcast frames. So it has to be 0 for you to accept broadcast messages. This ALBO, we have to be 0. Whenever you receive a broadcast message, this signal automatically comes on, the broadcast itself comes on, and if your ALBO is 0, you are going to receive the broadcast message. Then we also have this we call it a ALPO. ALPO means promiscuous mode. Promiscuous mode means you are receiving all frames, even the ones that are not sent to you. Every single frame is being received, whether it's broadcast, whether it's unicast, whether it's multicast, whether it's sent to you or not. You receive every single frame that comes around your way. That is, when you set this in your register ALPO, that is promiscuous mode. That means you are listening to every frame, you are receiving every frame. That is, you are more like eavesdropping to other frames that are both sent to you and not directed to you. Then we have the passor. This passor here. This passor, we are going to use this passor during the MAC control, when we'll be talking about the MAC control model with this control from address OK. This second signal here means control frame address OK. That is doing MAC control. We are going to see how we are going to use these two signals. The passor, we use it doing control frame. It means that you want to accept all types of frame. Here we have the normal data frame and also the control frame. We use the control frame doing when we are operating in full duplex mode. If we are in full duplex mode, we use control frame to say accept, to pause, and don't worry, when we be talking about the mark control model, you see how we use this password and control frame. So they are basically used to accept control frames. So then again, this is the multicast. This is the multicast address check. It checks for multicast. It uses the hash algorithm to check for multicast. I'm going to talk about this when I will be talking in the last tutorial, when we be talking about when we talked about the CLC error checking. You're going to see how these CLC hashes are being generated in another tutorial. How the CLC hash is being generated. This multicast signal means that you turned on the multicast signal on. That is, you are accepting multicast data. And if the CLC hash is good, you see how this is also generated. So this bit, we call it that the multicast is okay. This signal here means multicast is okay. So what this particular check here does, let me show you what happens here. So let's deal with the first NOR gate, that is this one. Let's see what this one does. This one first, because that is what sets this address miss on. So this address miss means that the address is not directed to us. That the address of the frame is not directed to us. It's different from RS abort. You will use this address miss doing when we'll be talking about control frame. That's when we'll be using the address miss. So how do we turn on this address miss? It means when we are in byte count 0, that is at the initial beginning of our counting, set it to 0. Initially set it to 0. Then this is how we turn it on. We use this AND gate to turn it on. We turn it on whenever we finish receiving the whole MAC address, that is at byte count 7. We've received our 48 bits of our MAC address, and when we are in state data, that is when we are receiving data, because you know that even when we are in state preamble, we have byte count 7 in state preamble, because we also count the bytes during state preamble and we reset it at the beginning of the state data. So this is going to telling us that when we have counted byte count 7 during data reception, not during preamble, that is, we've received the first 7 bytes of our data reception, that is when you are going to check for address miss. You check for address miss when you've received the first 7 bytes of our received data. So this is how we check it. So it says if is a broadcast 1, if is a multicast 2, if is a unicast 3, and if there is not a control frame 4, set it to 1. That is if is not, because this is a NOR gate. If is not a broadcast, if is not a unicast, no, if is not a broadcast here, if is not a multicast, if is not a unicast, and if is not a control frame, set your address miss to 1. Now let's see how we get our RS abort. How turns on this RS abort here. This is the AND gate. This AND gate here is what is used to turn on this RS abort. So let's see the condition for turning on this RS abort. One is that, let's see, it has to be within the state data, and it must have reached byte count 7. So whenever it's in state data and you've counted reached byte count 7, it means you have received the destination MAC address. That is what it's trying to tell you. That is, you finish, that is, check this address miss and check this RS abort after reception of your destination MAC address. Now the third condition is this one here. Okay, let me make a little edit here so you see what I'm trying to do. So this is still the same with what we did earlier. It still did the same check, because this, it means whenever it's in state data and it's byte count 7, and this last condition, let's see what this last condition tells. It says if it's not a broadcast address, if it's not a multicast address, if it's not a unicast address, and if you are not in promiscuous mode, set your RS abort to 1. RS abort means abort the data reception. Cut it. Abort data reception. That is what the RS abort does. So I promise you, I'm still going to come back to the multicast in a later tutorial to explain it more. So you can find this code here. The code is found here, projectfpga.com/tcp. You see the RS address check code here. So if you go through this code and go through this tutorial, you'll be able to understand perfectly how the receiver checks for the receiver address to know, does this address belong to me? That is, should I receive this frame or should I abort it? Thanks.